And as I have said, the pyrazinamide is thought to be converted to pyrazinoic acid, which changes the pH within the cell, and therefore that is how it's thought to bring about its mechanism of action. Mechanism of action. So you have the pyrazinamide going to pyrazinoic acid, and the pyrazinoic acid has an influence in or has an inhibition of the mycoric acid synthesis. Even by change of the pH, it influences the mycoric acid synthesis. It disrupts the cell membrane integrity because that pyrazinoic acid lowers the pH. There is acidity within the cell, and that disrupts cell membrane integrity. It also interferes with mycoric acid synthesis, and of course, it has the tuberculoidal effect by doing those two things. So that is pyrazinamide, that is our pyrazinoic acid, and that is what, as we have said, is thought to have activity. Pyrazinoic acid, highly effective in acid environment and inflammatory condition. And so PZA, honestly, the pyrazinoic acid is highly effective in acid environment and inflammatory conditions because the drug penetrates the membranes even much better when you have inflammation. It is well absorbed. It crosses inflamed meninges. It crosses inflamed meninges and is an essential part of the treatment of tuberculosis meningitis. It is metabolized by the liver, and the metabolic products are excreted by the kidneys. The metabolic route constitutes of the hydrolysis by hepatic microsomal pyrazinamidase, as we have said. So that is oxidation into pyrazinoic acid, which may be then oxidized by xanthine oxidase to 5-hydroxypyrazinoic acid. We have already mentioned that. And the latter compound may appear free. So because the pyrazinoic acid, high level, it has a carboxylic group, it has a hydroxyl group there, high water solubility, and therefore readily excreted. This we had already mentioned of how it is excreted or how it is metabolized, either to the pyrazinoic acid and then, of course, to hydroxylation. And once that happens, then it can have high level. We have also said glycine conjugation. Or remember, all you want to do for excretion is to increase water solubility. Once you increase water solubility or increase hydrophilicity, the drug readily leaves the body. Adverse effects. The most common, approximate 1% side effect of pyrazinamide is joint pains, that is arthralgia. The most dangerous side effects of pyrazinamide is hepatotoxicity. Remember, we did say during its metabolism, you can develop the reactive metabolite, and that reactive can bind the reactive metabolite, can bind the tissues or cellular tissues in the liver. And once it does that, it can cause hepatotoxicity. The others, you will definitely mention them when you look at your pharmacology. The most important for us is to understand the hepatotoxicity, because the hepatotoxicity comes about because of the metabolism. So it is a metabolism. It's metabolism dependent toxicity. Metabolism dependent toxicity, where it occurs when the drug is metabolized, and once it is metabolized, it can form the very reactive metabolite, which can react with the cellular of the cells of the host, bringing about toxicity. So there we are. So if you look at it again, we are just emphasizing on what we have done. So that is our pyrazine ring, and you add a carboxyamide. So this is our carboxyamide there, and once you add your carboxyamide there, and then of course metabolism to the carboxylic acid through hydrolysis. There's hydrolysis there, so hydrolysis of the amide to give us the carboxyamide. So contains pyrazine ring in its structure, which is a 6-membered heterocyclic ring containing 2 nitrogens, and you can see that at a distance of 2 carbon atoms. Pyrazinamide has an amide at position number 2. We are starting from there, position 1, position 2. It has an amide at position number 2. Remember, when you number, the substituent must carry the lowest numbers possible. So we are only looking at the structure and the SAR of pyrazinamide. Activity is pH dependent, and maximum activity takes place at pH 5.5. All we are saying is that once you convert, it is essential for this drug, first of all, to be converted into pyrazinoic acid within the microorganism to lower the pH. Remember, the pH normally is 7.4 of the host cells. So it is converted, lowers the pH, and that is when now it will bring about its activity. It can be considered a derivative of isonicotinic acid. Isonicotinic acid has one nitrogen, while pyrazinamide has two nitrogens that we have already looked at, or even a derivative of nicotinamide, whichever. You will only illustrate which change has occurred. Both are called isosteres, those having same biological and physical chemical properties, and they have also the same atomic numbers. So molecules or groups of molecules that have the same atomic numbers when you add them, and have also the same biological and physical chemical active properties are the ones we have been mentioning or calling isostere. Nitrogen has an atomic number 7, CH also has a 7, hence the isosteres, and they seem to also be responsible for similar activity. Hydroxyl group of isonicotinic acid or pyrazinoic acid is isosteric with NH2 group of PZA because both have, again, atomic. We're only looking at what's an isostate. It's those groups that have the same atomic number and also seem to have similar physical chemical properties and also similar biological activity. We have mentioned them before. So we are looking at that is our pyridine as found in isoniazid, as found also in the isonicotinides. All we are saying is that this, for pyrazinamide, the nitrogen requires to be para or separated. The two nitrogens should be separated with two carbon atoms. If you separate them with one carbon atom, or if you separate them with one carbon atom, then the resultant molecule is less active. So when pyrazine ring is replaced with an alternate heterocyclic ring, e.g. pyridine, so if you put a pyridine instead of the pyrazine, or pyrimidine is like this ring when the nitrogens are separated with one carbon atom. So when they are separated with one carbon atom, this is pyrimidine, the compound becomes less active. So if you replace the pyrazine ring with pyridine, or you replace it with pyrimidine, the resultant molecule is less active. Pyrazine ring is monosubstituted, while the substituted derivatives are less active. So again, unlike in the nicotinamides, like in the nicotinamides, where we did say you require dye substitution for the pyrazinamide or PZA, there should be mono substitution. That is the only one group that we have usually at that position. That is the only group that's allowed. If you do dye substitution, like again in the nicotinamides, again the activity will be much, much, much lower. But when further structure activity relationships were done, it was also found that you could do dye substitution, but with a little bit of more change, not just changing this. It was found that you could do a dye substitution, but if you did dye substitution, then you had also to do much, much more structural change. So with time and more serious structural activity relationship studies, this point was almost negated. That point was almost negated because it was found you could do dye substitution on the pyrazine ring. Remove that there, and you could do dye substitution, but the dye substitution also required that you do a lot of structural modification to the molecule, and that is what we are saying here, that it was found that you could do dye substitution. You see this to our pyrazine. There is a chloro substituent at that position, and you can see C double bond O, our amide is this one. But as I have said, you can see you have done a lot of substitution. You have added a tert butyl. You have added a tert butyl group there, and you have added a chloro group there. So there, it was found that if you are to do dye substitution, there's the structure required to be also more structurally modified for the resultant molecule to have activity. So that was one molecule that was found to have anti-TB activity, 5-chloro-N isobutyl pyrazinamide, 5-chloro-N isobutyl pyrazinamide. So that one. Another one which was found to have activity, which is also a dye substituted molecule, is this molecule here. You can see again the chloro group is maintained, the amide, and that's why we are saying it's a PZA derivative. That is that, and then you can see you put that group there, And then you can see these are very huge. This is really increasing. This group there is increasing the lipophilicity of that molecule, increasing the lipophilicity of that molecule, just as this group is increasing the lipophilicity. So you could also have 5-chloro N2-methyl dicyl pyrazinamide. Dicyl means it has 10 carbon atoms. If you look at this one, once you can see this is 7, 8, 9, 10, because it's carbon. So it's 1, 2, 3. It be 10. 5-chloro N2-methyl dicyl pyrazinamide. Dicyl is 10 carbon atom side chain. So side chain C double bond O NH. So it's 1, 2, 3, 10. 10. Methyl. Oh, okay, yes, I see why. Because we're already giving it the name N 5-chloro N2-methyl. So the methyl, we will not count one methyl. I was wondering why am I getting 11. So 5-chloro N2-methyl. So we will not count one of these methyls. We'll only count one. So it's one, because already we have mentioned one methyl as a substituent. So we'll count 1, 2, 9, 10. Yes. So the side chain is actually 10 carbon atoms. So 5-chloro N2-methyl dicyl pyrazinamide. If we look at these molecules, we can ask ourselves, what are the main structural changes? And the main structural changes in these two molecules, one was to ensure that that molecule has good lipid solubility. So you can see this molecule is adjusted in such a manner that it has very, very good lipid solubility. Why do you require good lipid solubility? Of course, you require good lipid solubility for that molecule to be able to penetrate the lipid membranes to give us good activity. Number the other requirement for this molecule was that it, of course, it had to have sufficient hydrophilicity and the hydrophilicity, and for it to have water solubility, or what you're calling the hydrophilicity, it has a carbonyl group and it has a two nitrogens within the pyrazine ring. And of course, you always have molecules must always have water solubility, so that they can be distributed throughout the body. So it had to have water soluble. The molecules must have sufficient water solubility. They must have sufficient lipid solubility, and also the structure. The structure must be such that it is stable enough. This molecule, it is stable outside this action. So these molecules were also made such that they were stable, very stable outside the site of action, until they get to the site of action, where at the site of action they were converted to the active moiety, which is a pyrazinoic acid. So remember that this molecule should not be converted to pyrazinoic acid outside the receptor. So we are saying that this molecule had retained three very important characteristics or qualities. One, it has to have good lipid solubility, and that is why there is addition of these huge hydrocarbon portions. When you you improve the hydrophilicity, or when you improve, not hydro but lipo, when you improve the lipophilicity is the lipid solubility. When you improve the lipophilicity or lipid solubility, the molecule can penetrate all the molecule can penetrate all the lipid membranes, and will get to the site of action in very high concentrations. So that's one characteristic these molecules are. These are the molecules that were later developed, which were bi-substituted, unlike PZA. The other thing is that we are saying they have good hydrophilicity or good water solubility, which is maintained by the amide group. That amide group is hydrophilic, and then also you have the two nitrogens. So those groups, the polar groups, will maintain water solubility in this molecule, because you require a balance between water solubility and lipid solubility to go into solution, and for the molecule to be available, or for bioavailability. So of course, the molecule had to have reasonable water solubility. The other a very important characteristic that had to be maintained is that these molecules are stable outside the site of action, outside the site or the receptor. They had to be stable outside the receptor, and they are supposed to get to the receptor intact, where they'll be converted. And of course, the receptor is within the Mycobacteria tuberculosis. Once they get into the Mycobacteria tuberculosis, that is where they are supposed to be converted to pyrazinoic acid. Because if they are converted to pyrazinoic acid outside the receptor or outside their active site, then definitely they are going to be excreted and the drug will not have any activity. So those three characteristics had to be ensured, or these drugs had to be synthesized in a manner that they have those three characteristics: good lipid solubility, good water solubility, good stability, such that they are not converted into the active moiety, which is a pyrazinoic acid, outside the receptor, so that, of course, they can bring optimum activity by being converted into pyrazinoic acid within the surroundings of the receptor and therefore bind the receptor very, very effectively. So these drugs, as I had said, were discovered much later, and therefore they negated the point we had said that dye substitution of these drugs or dye substitution of the pyrazine ring resulted in inactive molecules. Again, do remember when you put a chloro group, again, it stabilizes this ring against oxidation, against of oxidative aromatic hydroxylation, and again, giving these molecules slightly longer, a lot of stability, slightly longer duration of action in the body, and ability of these molecules to travel and get to the site of action where they will be converted into their action. It is effective against dormant Mycobacteria tuberculosis. Most of the others we have seen, they are not active against dormant. They usually are active against active Mycobacteria tuberculosis. Activity is pH dependent. We have already said that when administered, pH is lower to 5.5, which is not suitable for the growth of the Mycobacteria tuberculosis. Their growth is suitable at pH 7.2, hence Mycobacteria is eradicated. Is just one way of their activity, is where it is thought that by decreasing the pH, that pH is not suitable for the survival of these microorganisms. Of course, it is also thought, as we had mentioned earlier, to disrupt, of course, the acid or the change in pH will disrupt the cell membranes or the cell walls and bring about permeability. Also, this drug is also thought to a small extent also to have an influence on the mycolic acid synthesis. But one of the major routes of modes of metabolism is just that of lowering the pH and therefore disrupting or changing the pH which is necessary for the survival of this microorganism and bringing about its death. I think that is the end of PZA. That's our PZA, and that is the end of our PZA. Not unless if again there is any question. Pyrazinamide, active against dormant Mycobacteria tuberculosis. You combine it with isoniazid, with rifampicin, and it shortens the duration of drug administration. The shorter the duration, the lower the chance of development of resistance. The lower the chance of development of resistance because there is much lower exposure. But as I have said, 6 months is not very short. These drugs, and you're not taking one, you take them like their food every morning, and of course they have their toxicity. But what would one do if you have the TB? TB will, if not treated, will kill you. So it's better to withstand the toxicity of these drugs. It is better to adhere. What you need to, when you talk to patients, in case you are dispensing these drugs, it's good to make them understand. It's good to talk to them in the language they can understand, because being asked to take drugs for 6 months, it's not an easy thing. And of course, as I have said, these drugs have a lot of toxicity. There are many. There's combination therapy. There are many. They have a lot of toxicity. But the choice, what choice does one have? You take them. Of course, if you take them properly, you'll be cured of TB. You don't take them, then it is death. Not only is it just death for you, if you don't take them, and of course, or you do not adhere to the regimen, you take them badly, then not only is there danger for you, there is also danger for your family. because the mycobacteria, the TB microorganisms that you will pass on, because if you don't treat them properly, that organism will still be infectious. But the microorganism you will pass on, either to your significant few or to your neighbors, will be multi-drug resistant. So you can see the danger, and that's why is information, passing of information to the clients or to the patients when you are giving them drugs for TB is very critical. It might mean them taking the drugs or not taking them the drugs. And if they don't take the drugs or they take them the wrong way, the danger is by the time they die, they will have really messed a lot of people because they will have passed on the drug resistant TB. Of course, also, why would we lose anybody where and drugs are available, and it's an issue of just taking a few minutes and talking to them. And that is why more often than not, in almost every hospital, you do not mix. Of course, the disease is infectious. It also requires special treatment of the patients. So you normally have a TB clinic. A TB clinic, which, like, you have HIV clinic, you have a TB clinic, which usually even stocks the drugs. It stocks the drugs, and there is usually continuous medical education every morning for the patients every morning in that clinic before the drugs are given to them, before they are seen by the doctors, before the drugs are given to them. There is continuous medical education where they are even told about how should they feed, how should they take these drugs, how perhaps if necessary when they cough they must always cover their mouths and so on and so forth, and even when they sneeze, just to make sure that that disease is not passed on. Of course, within the first 2 weeks, there is supposed to be isolation. After diagnosis of this disease, there should be isolation, because after the first 2 weeks of good treatment where the patient appears, then the disease is no longer infectious. But within the first 2 weeks, it can be infectious. And of course, again, when one patient or one person within a family is diagnosed with TB, then you call the whole family, because you do not know whether any of those others have been actually have contracted the disease from the person who already has the disease. So again, you must look for the contacts, and again, tell them the reasons why you want to test them for TB, and so on and so forth. Of course, it used to be called the disease of the poor, but I doubt now it's the disease of the poor. Anybody, even the rich these days, they can get TB. They might not get pulmonary TB, but you might find they have another TB, another TB. And as we said, it can be TB of the brain, it can be TB of the bones, it can be different types of TB. So I don't think really, of course, it is more in areas of poor people, because again, there's a lot of congestion. This disease is really spread where you have a lot of congestion and so on and so forth. And as we have said, you need to take care of yourself. If you feed well, you will have enough immunity. So most of us do have these microorganisms within our tract, upper respiratory tract. But because we have good immunity, we are able to fight off the microorganism. But if your immunity goes down, is when you do have a big problem. And therefore, proper feeding and nutrition is also very important for these patients. So I think we are done with those derivatives, both derivatives of nicotinamide, where we have done INH, we have done the thioisonicotinamide, we have done PZA, and I think that is enough. So we want to look at another now different category of drug, or another drug which has a completely different structure from what we were looking at. So we are through with the nicotinamide derivative. So we're looking at ethambutol. I'd asked you, I don't know whether you're able to do so, to draw the various stereoisomers of ethambutol. If you look at ethambutol, this is the structure of ethambutol. So this is the structure of ethambutol. It has an acyl amino, acyl diamine. So that's the acyl or ethyl diamine, which is of course aliphatic structure. Then you can see this section. Actually, you can divide it here, you can divide it along here. And if you divide it along here, you find that this portion here and that portion there is actually the same. So we can, if you were to divide it along this line here, We can call, you would call that our internal mirror within the molecule. Internal mirror there, this portion there, and that portion there is the same. And because this portion on this side, dividing it again here, because this portion and this portion is the same, this, if you put your mirror here, you will get that this one on this side will be a mirror image of this one on that side. So they are mirror images. And not only are they mirror images, because of the structural similarities. If you look at this carbon, it has a CH2, OH, CH2, CH3, hydrogen. This carbon on this side is repeated. It has a CH2, OH, CH2, CH3. CH2, CH3. Because of this structural similarities on both carbons joined to the nitrogens, then you find that when you divide it here, the two groups are also what we call superimposable. So you can impose one on the other. If you in fact, if you get your mirror image, you get it this way, and they are also superimposable when you get your internal. When you get your internal mirror, you find that the two portions can lie on top of each other. And therefore, because of that fact that this portion and that portion other, when you have isomers or stereoisomers, which are mirror images and are also superimposable, we call them mesoisomers. Mesoisomers are those that are mirror images and superimposable. Superimposable is that where the two portions can lie on each other. Two portions lie on each other when the two portions are actually the same in terms of in terms of the substitution. If you look at the other isomers that we have been looking at, the dextro and the levo, we say those enantiomers are indeed mirror images, but not superimposable. It is that you can never take one and put it on top of the other. You will always find that the substituents are facing different directions. So the difference between the mesoisomers and the other dextro and levoisomers is a dextro and the levo, which we also call the enantiomers, are yes mirror images, but not superimposable. The mesoisomers and superimposable. And therefore, because of the fact that they are superimposable, then you find that this portion here could be having, if this portion is giving us is the levoisomer, this other one will be the dextro. So that this portion is the dextro, that will be the levo, and they will cancel each other with optical activity, and therefore mesoisomers have no optical activity, as opposed to dextroisomers. Remember, the dextroisomers are dextro because when you bring in polarized light, they'll deflect it on one side, when in fact to the right. The levo ones will deflect the polarized light to the left. Now these ones, this one of the chiral centers will deflect it to the right. The other one will deflect it to the left. After all, they are the same kind of chiral center. They have the same substituent. So one will deflect to the right, the other one to the left. They will cancel each other, and therefore the mesoisomers have no optical activity. So when we look at subital, we have the dextro enantiomer, which is positive and which also carries the S. The configuration is much more potent than the meso. When you talk about the meso, we have said the meso is the one whereby they are superimposable mirror images. Levoisomer is pharmacologically inert. Structurally, it possesses aliphatic diamine, that is the aliphatic diamine, and two butanoic moieties. That's a butanoic moiety. That's the butanoic moiety. Butanoic, we are calling it butanoic, of course, 1, 2, 3, 4. So we are saying it has that butanoic moiety 1, 2, 3, 4. Again 1. So again 1, 2, 3, 4. So that is a butanoic moiety. This is a butanoic moiety, and both the two butanoic moiety each joined to the nitrogen of the ethylene diamine. So once you say it is consists of two butanol and an ethylene diamine, then you already know the structure. So we are saying its structure possesses aliphatic diamine and two butanol moieties. It is a water-soluble bacteriostatic agent that is readily absorbed following oral administration. Stereochemistry.